Hello and welcome. Today we're going to be talking about partial derivatives where we left off last time. And we're going to highlight this concept called sensitivity analysis, which is a way to use partial derivatives on systems. So what's really important here is we typically have some sort of function that's going to be z is equal to f of x comma y, or maybe some other output that's some function of lots of inputs. So you could have x1, x2, x3, and so on and so forth. So what one does in practice is once a formula like this is obtained, we want to know basically what's the sensitivity of changes to xi variables on the output. Of course, that can be gotten by examining the size of those quantities, examining values. All right, so let's just go through two examples. So this comes from, these are related to section 11.3, problems 79 and 80. We're going to do variants of these. We're going to do variants of these problems, just going to show you things about them and how to do them. Okay, so let's go to the next page. So let's talk about, so there's a formula for parallel resistors. Okay, so you have some sort of battery like this. And then you have three resistors in series like this. Okay, so you have R1, R2, and also R3. Okay, so we want to know what's the total. So the question then is, what is the total resistance? So we'll call that question one. What is the total resistance? Of course, what we really need, the answer to that question is actually what you do is that you examine the inverse of resistance, which is conductance. Okay, so the formula is, of course, Gi is equal to 1 over Ri. So it turns out the total conductance is the sum of individuals, the individual conductances. So it's going to be G total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. And that makes sense. You can think of it like opening up a new channel. You can think of, if you think of a circuit as sort of like water, if water is flowing down this river, starting from a high point and going to a low point, we can think of basically the three channels as being different channels opened with different sizes, right? And of course, if I make one of these resistances smaller, I'm increasing the conductance, and that allows more through. So we can think of it as like that. The total conductance is the sum of all the individual conductances. So that's the same thing as G1 plus G2 plus G3. Okay, right, and that is equal to 1 over R total. Okay, so that means R total is going to be equal to 1 over 1 plus R1, 1 plus R2, 1 over R1 plus 1 over R2 plus 1 over R3, all in the denominator like that. All right. So the next thing I want to do is, the next question we want to ask is, let's compute the partial derivative. We're going to find this one, the partial derivative of R total with respect to R1. Okay. So what we can think about this is we want to know what happens, what is the sensitivity, what is the change in the total resistance when I change one of the individual constituent resistances. Okay, so we just have to compute these derivatives. And the plan here, of course, is pretty straightforward. Those two, we're going to consider those as constants. Okay, and only that's the variable. Okay, and by doing that, we just take the derivative like we would normal. So let's get a new page. All right, so we have here, I'll write it up again, R total is equal to 1 over 1 plus R1, 1 over R2, plus 1 over R3. Okay, and we take the derivative as follows. I like to think of it like this. We clearly have a chain rule type situation going on. And we're going to have negative, undo that. A negative 1 comes down. We'll get a negative 2 there. 1 over R1 plus 1 over R2 plus 1 over R3. And then we have to multiply by the derivative of this one right there. Okay, so we have to take the derivative of that, which is going to be negative 1 times 1 over R1 quantity squared. All right, so now we've taken the derivative of the inside. We've completed our chain rule. Let's do a little simplification. This becomes 1 over R1 squared all over 1 over R1 plus 1 over R2 plus 1 over R3 quantity squared. Okay, so that's our derivative. So that we've computed our partial derivative. Now what I want to do is do a little bit of sensitivity analysis. Let's examine the case that R2 is equal to R3 is equal to 10 ohms. Okay, and then I want to examine the two cases. I want to look at the case that R1 is equal to 1 ohm. I'll call that the first case. And the second case will be R1 is equal to 100 ohms. Okay, so I want to know what's the value of the derivative, how sensitive is the total resistance to when the resistance is small versus big. Okay, so let's figure this out. Let's look at case number 1. Okay, the partial derivative of R total over the partial derivative of 1 per the partial of R1 is going to be equal to 1 over 1, 1 plus, we're going to have now 2 tenths, okay? And that's going to be the same thing as 12 tenths in the bottom over 1. So that's going to be equal to 10 twelfths. So that's less than 1. Okay, so again, this is the case for R1 being equal to 1. We've got this... let's now go on. I'm not going to worry about it being less than or greater than 1. Let's just go to the other one now. Let's go to case 2. Let's look at R1 is equal to 100 ohms. Okay, what's the sensitivity going to be here? We can compute it. The derivative of R total per the change in R1 is going to be 1 over 100 squared, which is going to be quite a bit. and then we're going to also have 1 over 100 here, plus 2/10. And then what we have to do is multiply that by 10 on both top and bottom, and then we're going to get 21/100ths down there. And we're almost done here. What we have here is we have 100 in the numerator times 21 times 100 squared. Those will cancel, and we're going to end up with 1 over a very big number, so that's going to be 2,100, like that. So of course this is very small. Okay, so the total resistance is way more sensitive when the resistor is very low resistance. What this really means is, of course, is that a low resistance means there's lots of conductance. So any change in that resistor's conductance from near 1 is going to have a big impact on the total resistance. But if the resistor is very tiny, it means there's very little flowing through it to begin with. And so any changes you make to it won't have a big effect on the total flow through it. Again, it seems non-intuitive because there's lots of inverse relationships here, but when you think of it in terms of a river that splits into 3 channels, if you have a very tiny channel, if you change it very much, it doesn't change the flow of the whole river. But if you have a very big channel, i.e. low resistance, any change you make there is going to have a massive change in the total resistance of the river. So that's a cool problem, and I think it's non-intuitive, but it shows us a little bit about partial derivatives and how they're used in practice to analyze sensitivities of systems. All right, let's go on to the next problem. Let's talk about, this is going to be number 80. This is going to be related to a ideal gas law. The ideal gas law states this. Oh, sorry, no, this is an ideal gas law. This is related. It's called the van der Waals. The van der Waals equation. Okay, which is related to the ideal gas law, and it says this, that nRT, okay, and this is some gas parameters. Okay, and this one right here, that is temperature. Okay, and that's equal to P, that's the pressure, plus N squared times A over V squared, quantity times V minus NB. Okay, so here V, in this particular case, that's going to be volume. That's the volume in which of gas. Okay, N is the number of moles of gas in V. Okay, and R is that gas. It's called the gas constant. Okay, and A and B are just constants related to a particular gas. Okay, so it depends on the gas. So those would be parameters that you'd find experimentally if you're dealing with hydrogen or helium or argon or whatever. All right, so what we want to do is, so the goal is we want to compute partial derivative of t with respect to p, okay? We also, so that's the first goal. And the second goal is to take the derivative of pressure with respect to V, okay? We can imagine, let's just try to think in terms of a gas, what is going to be the change here. So if I just look at this one, if I increase pressure, what is the effect on temperature? Well, it should increase T. If you've ever seen a compressor work, they actually put off quite a bit of heat when you increase pressure, and that's because the temperature of the gas that you're compressing goes up. Okay, and then if I'm looking here, similar thing. What happens if I increase volume? What should happen to pressure? Pressure. Stop for a second and think. If I expand the volume, the pressure should drop. Okay, so we want to see what the sensitivity of this thing is. Let's see if we could figure this out. So you can think of van der Waals equation as a refinement of the ideal gas law. It has a few corrective properties. It works for things that aren't ideal gases. So let me let's just take our equation here. And I'm going to go to the next page. I'm going to paste. Okay. So there's our thing, and now let's take those derivatives. I'm going to go back a page and figure out, okay, we'll do a partial of t with respect to p. Okay, we want to take the partial of t with respect to p first. Remember that basically r and n, those are constants. Okay. And so we should be able to just divide them over and take the derivative with respect to p of this thing, of 1 over nr times p minus n squared a over v squared of v minus nb. All right, so that's what we want to take a derivative of. That's a constant right there, so it doesn't matter. Yep, okay, so we should be able to do this just fine and figure this one out. So we do have here where does p show up in this equation? It really only shows up in one place. So what I want to do is really take this factor and multiply it into both of these terms here. Like that. Hold on, I'm going to back up here a little bit. The 1 over nr can go right out front. I can take my derivative with respect to p, my partial derivative, and bring that right in. And now what I have here is I'm going to just multiply through these things. I have a p times v minus nb, and then minus n squared a over v squared times v minus nb. Note here that there are no p's here. Okay, so that's basically just a constant with respect to p. Okay, if p is our only variable, so really our derivative is quite simple. We just bring that in, and what we're going to get is 1 over n times r of v minus nb. That's it. Okay, so that's our final answer for that version of the problem. Now let's go on and do the other one. So I'm going to go back. We're going to do p with respect to v. So that was question number 1. Question 2 is we're going to now do p with respect to v. All right, so v is clearly a little bit more complicated. We're going to have to work a little harder for it. What we're going to do, though, is we are going to select. There is our equation right there, right? We want to get that and bring it down here. I'll put it right there. I'm going to clean it up a little bit. There's a few little... Okay. I'll just do a little bit more erasing here. Okay, that looks good. and we're going to take the derivative of that with respect to v, but we have to remember that 1 over nr is sitting right there as well. Okay, so now we have our pieces there. There's our p there. So we're taking the derivative with respect to v. I can see that the p is going to multiply into those two terms. So what I'm going to have here is a 1 over nr, which is sitting out front. And the derivative is going to move in. It's going to get this one first, and that's going to be equal to p, okay? And then I have to now look at minus and look at what's going on with this term here. So I want to now take the derivative with respect to v of this thing here. And now I'm going to take this, and I have to simplify it a little bit here. What I'm really going to do is say that's an n squared a over just v to the first power minus n cubed ab over v squared. Okay, so we should be able to get it here really soon. Okay, all right, I hope you can see that. Right here, we can move it up a little bit more. Okay. Okay, now let's go a little bit further here. We just have to take the derivative of this last part here. We have 1 over nr times p minus, and now we have to take the derivative. We can use the power rule. This is going to be a minus n squared a over v squared. All right, and then a minus, which makes a plus. N cubed a times b times 2 over v cubed. Okay, so that is our derivative that we've computed now. So it turns out that it's not clear to me that what we have here is negative. It probably depends on some very complicated factors here, but this is possibly negative. Okay, but it should be worth looking at this one as well, as I don't really know what the sign is without, we need to know the parameter b to know if this thing, and also n to know if this thing is negative or positive. It depends a lot on things like the volume and other things. So the van der Waals equation is a little bit more complicated than the ideal gas law. It has a few corrective factors in it that make it a little bit more elaborate. So I hope you liked this video. We did a lot of calculus in it, and I'll see you on the next video.